we're going to use our n behavior. That's going to be an important skill that we're always going to use. So we see that this is an x cubed graph, which looks like this. And in this one, we're going to use our intercepts to help us graph. X-intercepts and Y-intercepts. So how do you find a Y-intercept? That's the easy one. How do you find a Y-intercept algebraically? You make x equal to 0, right? The mental math that way would be 0 plus 0 minus 0. Okay. You could look at the constant term, which would work in this case. You have to be careful with that if, like in a parabola, when it's in standard form, the constant term isn't necessarily your y-intercept. So algebraically, plugging in 0 for x should be your go-to strategy. So the y-intercept is going to be 0. How do we find our x-intercepts? Algebraically, what you have to do? Make y equal to 0. Ooh. That's like a solving equation. How do you solve equations? You could first factor out the x. Nice. And we could factor this completely. Now this one was a very easy one to factor because there was a common factor of x to pull out. But what did we learn last class before the graphing one? We learned how to factor things fully with synthetic division and the factor theorem and the remainder theorem. So that's where this is connected. If we can factor things completely, then we can find out that your 3 x-intercepts are x equals 0, x equals negative 3, and x equals 2. Now, our one x-intercept and one y-intercept are exactly the same. They're at 0. But we would also have an x-intercept at negative 3. And notice I'm labeling negative 3 here so that I have a point there to give scale to my graph. And at this point, if I label negative 3, this is obviously 2, but I'm going to label that as well. And since the end behavior acts like a positive line, what do we know about our graph? We know that it comes from down here. Has to go through those points and end up here. And this is what this graph looks like. What we don't know about this graph is we don't know how high the local max is or how low the local min is. So had you drawn it like this, full marks based on those two. If you wanted to find out a specific point in here, like what happens at 1, you could plug 1 in like a table of values and use that to make it more accurate. 1 plus 1 minus 6 is negative 4. That's more accurate. So it looks like my purple graph is more accurate than my green graph. But I also made my minimum right at 1, negative 4. It doesn't have to be perfectly in between. So you don't know that for sure yet either. Answer these questions. Make sure you take calculus next year. So we're going to be okay with this for now. We're just drawing a sketch, getting the basic idea for the shape. If we want more accurate details, we can go to our graphing calculator. But the intercepts and the end behavior give us a nice shape.
If you're labeling your graph, like, would you get it wrong if that's not your local minimum?
No, at this point they're not going to take that off. If you leave it like this, you're not expected to find out where your local minimum is. The only way, if you wanted to find your local minimum, then you would have to use your graphing calculator and that function built into it. But for right now, whether you had it like this or you had it like that, where the local minimum is further over, that's fine. It kind of feels like, oh, it should be right in between there, because if you've been graphing parabolas and things happen nice and symmetrical, but they don't always work that way. So for this one right here, it was easy because the factoring was easy. If we would go to the example that's listed here that they gave, not so nice, but let's just look at it. For this one, you would have to start with your remainder theorem. So they tried a bunch of things. They found out that f of 1 was equal to 0. That means that x minus 1, here I'll highlight the key things as we go. So first of all, use your remainder theorem to find out where one of them is equal to 0. You then can say that x minus 1 is a factor. Use synthetic division. Since x minus 1 is a factor, you put a 1 out there. You should, with your synthetic division, get a 0 for remainder. And then you can write your division statement where things are partially factored. You now have it equal to x minus 1 times something. Now that something would need to be factored further. So now you've got a new function. You use your factor and remainder theorem again until you find out that when you plug in p of 2, you get 0, which tells you x minus 2 is a factor. Use synthetic division again. With positive 2 out here, you should get a remainder of 0. And so now our original function has our first factor, our second factor, and this left. And notice when they're writing the division statement, each time they're writing the whole thing. It's so tempting to do shortcuts here and not write things out mathematically correct. So we do want to write out the whole thing is equal to. And sometimes what I suggest to people, because especially this first one, it's long, right? If at the very beginning you say let f of x equal this, then you can just write f of x equals each time instead of having to rewrite the whole thing, which can save you some time. Once you get to a quadratic here, that just factors nicely, so we get our final thing. Oh, they did call it f of x. They wrote the final completely factored thing here. They made it equal to 0 to find the x-intercepts. And they've got 4 x-intercepts or 4 zeros. So now when they go to graph it, ooh, that was pretty. When they go to graph it, they can put those 4 x-intercepts there. They could easily plug in 0 for x and get a y-intercept. The end behavior of this one is like a positive parabola, so we know it ends up here and ends up here. Okay? Now chances are when you were graphing this, you would probably do this. Down, go through this one, through this one, through this one, and up. And that would be perfectly fine. You would not necessarily know that it goes way down there. Right? That black graph would be accepted for full marks. Only in calculus do you figure out exactly this value of the negative or using your graphing calculator to check it. Of course, if you were given your graphing calculator, why not just copy the graph from there to begin with? So that's why they accept the black graph or the red graph. Okay, so I do want you to try these. Try 7 and 13 where you factor to solve.